My name is Ethel Prus, and I'm a bachelor student in Tilburg University's Department of Cognitive Science and Artificial Intelligence. And so are my co-authors, Charles Princeton, Anita Vrins, and Katerina Cesaro, and Mariam Almardani is a professor in the same department. Today, I'm going to tell you about our proof of concept paper that looks into the possibility of combining robot assistants with BCI smart homes, which we investigated in a virtual reality environment. And we did this in collaboration with Mind Labs. Okay, so basically brain-computer interfaces are computer systems that use brain activity as input. A recording device, such as an EEG cap, is used to capture the user's brain waves, and these waves are then transmitted to a computer, which looks for patterns in the signal. And for communication interfaces, the pattern can then be translated into a letter or a word, or for control-based BCIs, it might be a task such as turning a light on in a smart home. And for patients with severe motor impairment, BCIs are used to restore the user's connection to the outside world, using devices that require hand movements for input, such as smart devices, might not be possible. And for some patients, it might not even be possible to use voice or gaze-controlled devices. And in these cases, BCI can be used for communication, entertainment, and control, controlling devices that influence the patient's environment to improve their quality of life. And one of the potential use cases for BCIs involves smart home environments, which is what we're going to be talking about today. There are several studies that show the possibilities in this domain. A 2021 study by Sahal et al. Looked at how BCI systems for patients with neuromuscular impairments, and particularly ALS, could be improved in the context of smart homes. They used augmented reality glasses to display BCI control options, which they found to be an improvement compared to screens, because patients could have trouble sitting upright to look at a screen for extended periods. The BCI setup was used to control Google Assistant, which allowed the user to control their environment in various ways. Another study from 2009 by Edlinkler et al. Tested out BCI-controlled smart home environments in virtual reality. This setup included a virtual home with various control options, such as controlling lights, a TV, and moving the view to different locations in the simulation. They found that about 80% of users could use their BCI smart home system within 5 minutes with no previous training, which is promising for wider use of similar systems. But the focus on these studies and other similar ones has been on controlling electronic smart devices that facilitate ambience and entertainment, such as lights, TVs, and music players. However, more basic needs, such as retrieving water, food, or medicine, have not been addressed. A potential solution for filling this gap could be adding robots to smart home environments. And robot-assisted smart homes have been studied, but not so much in combination with BCI. The focus has been on elderly care using smart devices such as tablets as an input method. For example, in 2016, Koseski and Koseska developed a telepresence robot aimed at the elderly and their caregivers. This robot could be driven around as well as grabbing and touching small objects with a robotic arm. And a tablet with a camera was attached to the head of the robot, so users could use the robot without being physically present. This could also be used for two-way video calls to stay in touch with caregivers and family. And participants reported their perceived functionality usefulness of the robot on a 5-point Likert scale. Both navigation and the manipulator functions achieved scores of 3.0 and higher, indicating high user acceptance, which is again promising. And another study in 2018 focused on elderly care in a smart home environment. It proposed an overall structure for a robot-integrated smart home, where the robot served safety functions, such as detecting falling sounds and providing assistance if needed. The robot could also track humans and monitor their activities to keep track of overall well-being. These robot-assisted smart homes seem promising, but they are meant for patients who are more mobile, or at least able to use handheld devices for input, and this would not be accessible for all motor impaired patients. So this brings up the question, could BCIs be used as a control method for robot-assisted smart homes? And there is not much research to directly address this question yet. We found one study by Spataro et al. In 2017, where a nanorobot was used to fetch a glass of water. The participants were mostly successful in completing the task, but the nanorobot is not capable of navigating outside of a small flat surface, so this required a desk or a wooden board laid over a bed, which wouldn't be ideal for use cases outside of the lab. Other smart home functionalities were not included in this study. This gap in research gave us the idea to develop a prototype that combines BCI controls, a smart home environment, and a robot assistant to create an accessible and optimally useful system for motor impaired patients. So to address this issue, we designed a proof of concept in virtual reality for a BCI robot-assisted smart home environment. And the system consists of a VR head-mounted display, seen in the left corner here, an EEG cap, again on the user, and a custom P300 speller board displayed on the VR display in the little corner in the bottom of the VR. All devices are wirelessly connected to PC, so the whole system can be moved easily or used in different positions. The VR device displays a P300 speller board with options for different tasks, and the EEG cap records EEG signals from the user's brain and wirelessly sends them to the computer, where after feature extraction and classification, the VR control signal is fed into the VR simulation as an input. The user then receives visual feedback in the VR device, which shows them their task selection was successful. And as you can see on the figure, the sequence of events creates a continuous loop. And we'll look at each component more in depth, starting with the P300 BCI component and the custom speller board that is used with it. Our system uses the Unicorn Hybrid Black EEG headset and software by G-Tech for recording brain activity, with the electrode placement seen in the figure B. And we use the P300 paradigm to facilitate user input. This means that we show the user a speller board where every possible task is represented as an icon. We made a custom one with household-oriented items. This is displayed as an overlay inside the VR environment, as seen in the last slide. So to make a choice, the user should focus on the icon they want to select and count the times when the specific item flashes. This elicits the P300 response, which can be detected in the EEG signal. And after a few flash sequences, the system can isolate which icon the user was focused on. We used 5 flashes in our preliminary tests, but more research is needed to see if this number could be lowered while still maintaining accuracy. The virtual reality environment the user finds themselves in consists of a single room studio with kitchen and eating areas, and this is meant to emulate a small smart home setup. There is also a virtual telepresence robot assistant, seen in the image labeled B. It can help with accomplishing tasks such as retrieving objects for a user or moving objects around, for example, for cleaning up. The user can use the controller board seen in the middle to move the robot freely in 4 directions or choose from high-level tasks that involve either a direct response from a smart device or a combination of smart devices and robot retrieval. For example, the light bulb icon directly turns the light on, but other tasks, such as making toast or cleaning up, also use the robot as a delivery method. There are 2 possible views in the VR environment. The first-person view, which would have the advantage of showing the robot's field of view even when it's out of range of the user. And the third-person view, which also shows the robot itself. And next, we'll watch a small clip from the development process, showing the prototype in action. Okay, so this is a video showing the virtual environment on a screen, which is controlled by an EEG cap with Katarina. It's a little dark, but first she uses the EEG cap to turn on the lights in the environment. And then she sends the signal to make toast, which makes the toast pop up as feedback. And then she will send a sequence of commands to move the robot to retrieve the toast. And this is done using the arrow icons. The robot is approaching the toast, and when it reaches the toast, to indicate that it has been retrieved, the toast will disappear from the toaster. Okay, so that's that. And there are some limitations to our research. It is just a proof of concept at this stage. And the main limitation is a lack of user evaluation and testing. A lot more user research is needed to bring BCI-driven smart robot-assisted smart homes from the lab setting to the real world, where they could help disabled patients. And given more time, we would have liked to include user research at all phases of design and development to ensure that the functionalities of the system match what the patients and their caregivers actually need and value, and that these functionalities are comfortable to use as well. And another problem point could be the trade-off between speed and accuracy for the P300 paradigm. Generally, more flash sequences yield higher accuracy, but this slows down the response time of the whole system. Especially for real-time robot control, it's important to find the sweet spot between good accuracy and low response times. For future research, hybrid BCI could be an interesting avenue. For example, the robot movement control options might be better optimized using the motor imagery paradigm instead of P300. And research using target user groups is also a potential direction for future research. Another feature that needs more development is switching from active and passive control of the system, so that the system can distinguish when the user intends to use the system to enter a control option or when they're just resting. For this, the P300 paradigm could be paired with gaze or attention tracking as an off-on switch. So to conclude, we have presented a prototype of a BCI robot-assisted smart home that consists of a head-mounted VR display, a wireless EEG headset, and a P300 BCI component with a custom smart home-oriented speller board. The prototype we presented also won a first place award at the Brain.io International BCI Hackathon, which is where this idea started. And while more development is needed, this VR prototype could serve as an affordable platform to design and evaluate smart home systems for patients with motor impairment, with the aim of restoring some of their independence and giving them more control over their living environment. So that is all from me. Do you have any questions?